Solubility of salts. Depending upon solubility of a salt in a particular solvent at a given temperature, salts are classified into three categories. First one, soluble. A salt is said to be soluble in a solvent if its solubility is, S denote solubility, if its solubility is greater than 0.1 molar. If the solubility of a salt is higher, that is more than 0.1 molar, the salt is said to be soluble in it. Now, if the solubility is very small, less than 0.01 molar, solubility of a salt in a solvent is less than 0.01 molar, it is said to be sparingly soluble. Sparingly soluble salt. If the solubility of the salt is between intermediate, that is less than 0.1 molar, and solubility is between less than 0.1 molar and more than 0.01 molar, the salts are called slightly soluble. So depending upon solubility, salts are of three categories: soluble, sparingly soluble and slightly soluble. Okay. Now we are going to discuss the solubility equilibria of sparingly soluble salts which have poor solubility. So let us consider a sparingly soluble salt, barium sulfate. The equilibrium, the solid barium sulfate, when we consider the saturated solution of barium sulfate, there would be an equilibrium between the solid barium sulfate and the ions present in the saturated solution. That means Ba2 plus in the solution, in the saturated solution of barium sulfate, there would be barium 2 plus ion and sulfate 2 minus ions. There would be an equilibrium between undissolved, that is solid barium sulfate, and the barium and the sulfate ions in the saturated solution. So this is the equilibrium between solid barium sulfate and its ions in the saturated solution. See, so this forward direction, it is dissolution, formation of saturated solution, formation of ions. In the backward direction, this ions present in the saturation gets back to the solid state, means solidification. Solidification process. The dissolved ions converted back to solid state, undissolved state, that is solidification. So there is an equilibrium between the two processes. If you write the equilibrium constant for this reaction, equilibrium constant Kc for this reaction can be written as concentration of barium 2 plus into concentration of sulfate 2 minus divided by concentration of barium sulfate. We know barium sulfate pure solid, concentration of pure solids remain constant, right? Concentration of pure solids remain constant. So this denominator is a constant. If that constant is taken to the left hand side, we get Kc into concentration of barium sulfate, which is equal to concentration of barium 2 plus into concentration of sulfate ion. Take constant into another constant, we get another constant. That constant is denoted as Ksp. Ksp is called solubility product. Solubility product of barium sulfate, denoted as Ksp. What is Ksp? It is the product of concentrations of barium and sulfate ion. In a saturated solution, the amount of barium ions or the amount of sulfate ion produced will be equal. The concentrations of barium and sulfate ion produced will be equal because as per this balanced chemical equation, 1 mole of barium sulfate, when dissolved, we get 1 mole barium 2 plus ion and 1 mole sulfate ion. If the solubility of the salt, solubility of barium sulfate is S. If S is the solubility of sulfate, barium sulfate, that is S mole dissolved. When S mole dissolved, we get how many moles of barium? 1 mole will give 1 mole barium, 1 mole sulfate. That means S mole when dissolved, S mole on dissolution, we get S mole barium ions and S mole sulfate ion will be produced. That is concentration of barium 2 plus ion will be S into concentration of sulfate ion also will be S, which is equal to S square. That is solubility product KSP is equal to solubility raised to 2 for barium sulfate. This is for barium sulfate only. This relation between solubility product and solubility will be different for different salt. It depends on stoichiometry of the equilibrium. So for barium sulfate, if KSP value given, solubility can be calculated. If solubility given, KSP can be calculated. This is the relation between the two for barium sulfate. Now let us take another salt, another sparingly soluble salt, lead iodide. Lead iodide solid. The equilibrium between lead iodide and its saturated solution. Saturated solution contains Pb2 plus ions and how many iodide ions? 2 iodide ions. This is the equilibrium between undissolved lead iodide, that is solid lead iodide, and the dissolved ions present in the saturated solution. If you write the expression for solubility product KSP will be equal to concentration of Pb2 plus into concentration of I minus raised to 2. The coefficient should come in the power of the concentration term. I minus raised to 2. Clear? This is solid. That constant is taken into this equilibrium constant, and that's why we got KSP. So this is the expression for KSP for this particular equilibrium. Now if S is the solubility of lead iodide, as per the balanced equation, 1 mole PbI2 gives 1 mole Pb, right? Pb2 plus ion, and 2 mole iodide ion, right? Therefore, S, solubility of lead iodide is S mole, no? S mole lead iodide will give S mole Pb2 plus and 2 into S mole, 2S mole iodide ion. Substituting here in the KSP. KSP is equal to concentration of Pb2 plus will be S mole into concentration of I minus 2S. 2S raised to 2. So what do we get? S into 4S square, which is equal to 4S cube. This is the relation for solubility product and solubility for lead iodide. KSP is equal to 4 into solubility cube. Here also, knowing one, the other one can be calculated. If you take one more example, zirconium phosphate. Zirconium phosphate, the formula, zirconium 3, phosphate 4 times. Zirconium phosphate. Solid, equilibrium with its saturated solution. Zirconium ion. How many zirconium ions will be there? 3 zirconium ions plus 4 phosphate ion. I have not written the charge on these ions now. In order to avoid the confusion with these numbers, I have not written the charge. Zirconium is positive ion, phosphate is the negative ion. Let us write the equation for solubility product KSP. KSP is equal to concentration of zirconium ion raised to 3, its coefficient, into concentration of phosphate ion raised to 4. Right? If S is the solubility, of zirconium phosphate, according to this balanced equation, 1 mole zirconium phosphate gives 3 mole zirconium and 4 mole phosphate ion. Right? Here the solubility is S mole, no? S small zirconium phosphate will give 3S small zirconium, right? And 4S small phosphate. Clear? So substitute this in KSP equation. So KSP equation will be equal to concentration of zirconium is 3S mole. 3S raised to 3 into concentration of phosphate 4S. 4S raised to 4. This is equal to 3 into 3 into 3, 9, right? 9S cube into 4 into 4 into 4, 56, right? 256 s raised to 4. So you will get the answer as 6912 s raised to 3 plus 4, 7. The relation between KSP and solubility for zirconium phosphate. Knowing KSP, solubility can be determined or vice versa.